Synthetic aperture radar or SAR technology is a great remote sensing sensor as it images the Earth's surface regardless of weather condition and lighting. SAR microwave radar waves can penetrate the canopy and measure the scattering and reflection pattern of the underlying terrain. It can detect millimeter level change on the ground and be sensitive to many bio and geophysical parameters of great importance to measure the state of our blue planet. In 2022, FDL developed a machine learning pipeline for landslide detection that used SAR. However, this model struggled to maintain high performance when applied to new location or times. This lack of generalization capability due to the complexity of SAR data has posed a hurdle in developing self-supervised learning techniques applied to SAR that can easily be adapted to multiple use cases. With this year's challenge, the Generalizable SAR team aimed to create a foundation model for analyzing SAR imagery and understanding the challenges of creating flexible but robust machine learning model for a variety of downstream applications. This included dealing with complex polarimetric and interferometric SAR data, generalizing across time and space domain, developing tooling to facilitate easy analysis and compelling visualization, and exploiting huge quantities of unlabeled SAR data coming from the European Sentinel-1 mission. Thank you to the SAR team researchers, faculty reviewers, and all our partners for supporting this worthy effort. Thanks.
Hi everyone, welcome to our team showcase. We are the Generalizable SAR team. Our lovely team members are Freddy, Raul, and Ana as our faculty advisors, and Laura, Joseph, Alejandro, Matthew, and myself, Francisco, as researchers. Our planet is suffering from many environmental problems, and the natural disasters are increasing in frequency and intensity. We are seeing more floods, fires, hurricanes, etc. We will have witnessed last month's temperature records all around the world. The scientific community is doing a great effort to understand and address these problems. For example, Earth observation is used to monitor the land to rapidly detect floods and fires and react to them in time. However, this takes a lot of time and effort and needs investment, computing power, access to the data, and expert knowledge. That's why we need AI. AI can help us to process this data and obtain insights from it. We are creating foundational generalizable AI models that can be used as facilitators to solve multiple tasks. We will help the community to improve their own research without the cumbersome process of creating their own models from scratch. We have different types of satellites. We have optical satellites that use the sun's light, and we also have radar satellites that use radar to collect data. And this is the satellite we are using to build our models, the Synthetic Aperture Radar, SAR. It is very useful because it can be collected at any time of the day and in any weather condition. Also, we can measure changes with millimeter precision. This is useful to monitor changes in the Earth's surface. For example, we can monitor the melting of glaciers or the movement of tectonic plates, or changes in structures, water content, and land characteristics. But SAR data is complex. It is not easy to interpret. It requires expert knowledge. It has different kinds of data, for example, amplitude and phase that can be used for interferometry. And the data is not always available for the same location. So we need consistent global datasets for SAR. And now Alejandro will explain more about those datasets we were building for this purpose. Thank you.
Thank you, Fran. Hi, I am Alejandro. Well, as Fran described it before, we built machine learning-ready datasets that can be used for a variety of SAR applications. Our data spans 6 locations, covering diverse SAR input data, including SAR amplitude, interferograms, and coherence, and many downstream tasks. But how can we derive valuable insights from this wealth of information? using machine learning, of course. But machine learning for Earth observation is hard. We have few labels available. And as the SAR team from FDL 2022 has shown, SAR models are geographically localized. They train a model for landslide detection on one region and apply it to an unseen region. The resulting model didn't generalize well. So what if we tell you that we are developing generalizable AI foundational model for SAR data that can be used anywhere and with any kind of input data? It is important to emphasize that the term foundational in this context refers to a model that has undergone extensive training using vast and diverse planetary images. To enable this possibility, we developed a flexible machine learning pipeline that allows you to utilize different SAR input imagery for pre-training models. This pre-training occurs without the need for explicit labels. Rather, the model is pre-trained solely using the images. Subsequently, this pre-trained model can be employed in various downstream tasks, included but not limited to vegetation estimation and land cover classification. These novel models can aid in Earth system monitoring and disaster response. I am now passing the voice to Matt, who will explain our promising results on studying vegetation, changes, and land cover and floods.
Thanks, Alejandro. So we've been talking about foundation models so far, but what did we actually do? So we went to the ML literature and we took 4 state-of-the-art foundation model architectures and we adapted them to SAR data. And broadly speaking, we applied 2 different kinds of special pre-training tasks. These are ones which don't require any human labeling. So for the first task, we take a single SAR image as input and we cover parts of it up and ask the model to imagine what might have been there before. For the second scheme, we take 2 SAR images as the input from different sensors, and we ask the model to guess whether these images from different sensors were taken at the same location. So let's start with one of the easier tasks, which is vegetation prediction. So all we're doing here for vegetation prediction is we take a tile of SAR data and we ask the model downstream after it's been pre-trained to then predict what percentage of this tile is covered by vegetation. So if I could direct your eyes over to the left, the only number you really need to pay attention to in these plots is the one in bold font just below the x-axis. And what that is the percentage of labels we needed downstream to replicate the performance of a baseline model that used all the labels without pre-training. So in the case of Europe, which is the top graph, this is a region that has been seen before during the pre-training. And in this case, we were able to reduce the need for labels downstream by 95%, which is exceptionally strong. On the bottom graph, this is South America, a region that has not been seen even during the pre-training, but only has used downstream. We're able to reduce the need for labels by over 99%. So we needed 0.8% of the original labels. But what does about 1% of the data actually look like? Well, if you look over to the left on this on your screen now, you should be able to see this picture of Europe, which looks sort of like it's got chicken pox with these red spots. Together, these red spots make up 1% of the total area of Europe. And if I was to take these and squish them into big blobs somewhere in the middle, it would be about the size of Switzerland, plus or minus 5%. If you cast your eyes now over to the right, on the top right, you can see our predictions of vegetation using the model that's trained only on the 1% data, and also what the vegetation actually looks like in Europe in the bottom right. Hopefully you'll have as much difficulty as I do in telling these things. Let's look at something slightly more difficult now. So one of the other tasks we mentioned was land cover, and land cover is an example of a task in machine learning that we call segmentation. And all that means is I'm going to go through the images and pixel by pixel, I'm going to sort the pixel into some semantic category and give it a label. So each pixel might belong to forest or a built up area or a river, etc. And again, in this case, in a region that we've not even seen during pre-training, South America, we're able to reduce the need for labels by over 90%. And again, visually in the bottom left, the predictions look fairly convincing, although you can probably tell them apart if you squint a bit. So the final task that we mentioned in our sort of preamble was flood detection, and this is something that is still ongoing. Now, flood detection is difficult, more so than the first 2 tasks, because it takes 2 images as input, one from potentially before a flood and one from after the hypervertical flood. Secondly, it's not quite as simple as just doing, say, land cover classification on 2 different tasks and then looking for the difference. So, for example, you may have standing water somewhere which is permanent, but if it gets deeper, but it still constitutes a flood. And thirdly and finally, there are some nuances regarding how the data is stored that make it a bit more difficult to deal with than the first two tasks. But this work is still ongoing, and initial results are extremely promising. We're making good headway, so please stay tuned for more information on this. Now I'll hand you over to Laura, who'll chat a bit more about the impact that we hope this work will have downstream on practitioners in the science community.
Thanks, Matt. I'm Laura, and our project will enable the availability of several machine learning-ready datasets, both from SAR data and from SAR applications. Also, a flexible and modular machine learning pipeline will be released so that the user will be able to easily change the data or the model if needed. And of course, the most important product of our project is the pre-trained models that will avoid the user train bigger models, which require high computation resources and time. This may allow them to obtain quicker predictions and will help, for instance, when managing the response of natural disasters. So we are now in the first step towards planetary scale Earth observation foundation models, where different types of data will be taken into account for a wide range of applications that will help us face the changing times that we are undergoing on our planet Earth. So community, are we ready to take our work to the next level and help us develop a foundation model that will predict anywhere, anytime, for any task and with any data? It is the time to show the world how AI will help us when helping others. And of course, this work wouldn't have been possible without the support of FDL, founders, and partners. Thank you.
Thank you so much, Laura. Thank you, Generalizable SAR team, for the fantastic presentation. We are now ready to move on to our faculty thoughts portion. And with us today are Freddy Calaitzis from Oxford and Raul Ramos-Boyan from the Universidad de Antioquia in Medellin, Colombia. So to get us started, we also have Anna Youngbluth with us. To get us started, Freddy, maybe you can answer what excited you most about this presentation?
Well, the big picture to me is that traditionally, the way we've been teaching computers how to solve tasks has been quite primitive, relatively speaking. Like we always have to give them what is the ground truth, and the ground truth is very expensive to acquire. We have to use expert knowledge. Now, in certain tasks, in certain real-world situations, we don't have enough budget or resources to acquire that expert knowledge. What we do is that we leverage the knowledge that we have as human beings. For instance, we know that we can learn a lot of things since we're born without requiring experts to label things for us. We can just use our own evolution. So somehow along the way, especially in the last 5 years, we have endowed computers with that ability. We can now kind of bootstrap the computers in a way that they can learn from a lot of data, satellite imagery, without requiring expert labels. And then we can rely on that ability to further fine-tune them by using expert labels for specific tasks like detection of vegetation or floods, etc.
Thanks, Freddy. Anna, would you like to add anything?
Yeah, of course. So I was very fortunate to be able to join the team as an advisor from ESA for the last 8 weeks. And I think looking at the team's presentation now and reflecting back on the initial conversations that we've had at the very beginning of the summer and the plan that we've set out for, the goals that we wanted to achieve over the summer, it's really been incredible to see how much work the team has managed to get done in these 8 weeks. And really resonating with what the heliophysics team has said, these 8 weeks are really very short, and actually it's less time that you can really spend coding. So to see all of this progress in really such a short period of time that all of these amazing researchers have done is really absolutely mind-blowing. And I think that just really shows how much innovative research you can get done when you provide environments for people to work together, to learn from each other and grow together. And of course, when you have compute resources like what we had available thanks to the wonderful partners. So yeah, it's a really great close to the summer.
I agree. Raul, what most excited you about the presentation today?
Well, for one, it is, as Anna just said, getting like the four state-of-the-art models of self-supervised learning to work in a single pipeline, in a single machine pipeline, is no small engineering feat by itself. But also this would have not been possible without the individual excellence of each one of the members of the team. That is key. The coherence that we achieved throughout the work. So it is not just 7 individuals in their caves and then coming up with whatever they do. What we have been, I mean, in terms of the methodology that the FDL puts forward for us, and it's been key. And of course, without the computer resources, this wouldn't be possible. I mean, without the Google Cloud platform and the NVIDIA DGX machines and the fantastic support that we have been getting from NVIDIA, this wouldn't be possible. But I think there are 2 things which I value the most. Well, one of them, it is the doors that this opens for the future. I think we are much more ready to train planetary-wide foundation models for SAR, and I think this in the long run is going to be very useful. But even beyond that, I think this has been a learning experience for all of us in the team, technically, organizationally, personally, and I couldn't be more proud from that.
Thank you, Raul. And speaking of the future, Freddie, what do you see as next steps for this research?
Well, in the world of machine learning, bigger is better. So if we want to handle planetary scale deployment, then we need to be able to handle this bigger amounts of data, which means we need more compute. But sometimes compute is not just the answer, it's not always the answer. Sometimes we have to be smart, and we should be able to handle more data, but more efficiently without necessarily requiring more compute. I mean, again, looking back at us, the way we function, we don't need 10 brains to learn about the world, right? So there's something very efficient going on that nature has figured out for us that is waiting for us to discover.
Thanks, Freddie. Anna, would you like to answer as well? What are you excited about for the next steps?
Yeah, I mean, I think Freddie and Raul have summarized it perfectly. Having now such a modular pipeline that we can scale up from to potential planetary scale foundation models is really, really exciting. But also the data sets that the team generated, it's close to 40 terabytes of data spanning 6 regions in the world, and you've seen the wealth of downstream tasks that we have data for. I think this is going to create a really nice benchmarking data sets for future efforts in this area. So very excited to see what the team makes of the current state of the project, and also where the FDL will take it in years to come.
I completely agree. And thank you all for your kind words, your encouragement.